Section 1.1 is titled A Preview of Calculus. And what we're going to be looking at in this section is just what makes calculus different from some of the other classes that you've taken in mathematics. How does it differ? Okay? So the first thing I want us to take a look at is the definition, or how we're going to describe what is calculus. Okay, so don't draw all these pictures. This is nothing I intend for you to write down, so just bear with me. The what is calculus, you have a place on your paper to write this down. Calculus is the mathematics of change. So what we're going to do in calculus is study and look at how things change. That's really what it is. Your book has a fantastic, and I'm putting it on several slides, but a fantastic visual. This is on pages 43 to 44, so I've written it down in your notes, that talk about sort of the difference between pre-calculus and calculus in sort of studying problems. So if you take a look at this first one, the left-hand side is going to say without calculus, and then the right-hand side says with differential calculus, okay? So if you have your book with you and you want to reference this is fine. If you just want to sit back and watch and kind of think through what the differences are, you'll start to notice some of these pattern kind of things. So without calculus, the first one talks about being able to find the value of the function, so that's like the y value of a function at a specific x value. So in other words, if I've given an x value, I can plug it in, I can find y. That's a pre-calculus idea. Algebra stuff, right? Yeah. Well, calculus looks at things like limits. What value do we get close to? Maybe we don't actually get at that value. Maybe when you plug in 5, it actually doesn't exist, right? That happens sometimes. You guys have seen that happen in pre-calculus courses. Well, that's what calculus does. Calculus allows us to be able to find what value sort of it should have reached, what value it got really, really close to. That's called a limit. Without calculus, we're able to find slope. We specifically find slope of a line, right? We take 2 points on it. We have this cool formula, y2 minus y1 over x2 minus x, and we find its slope, right? That's pre-calculus. You probably started it somewhere in middle school, okay? And then what calculus does is it allows us to find the slope of a curve, right? So this is straight, and this is curved. And so we do this by finding, somehow this other line, which has a name, we'll talk about in a sec. Find this other line and we find the slope of that, and we call that the slope of the curve. That's a calculus idea. We're going to encounter this one again down here, further along the way, lots of times. A secant line. Where have you heard secants before? What was it? Trig? Where else? Before trig, you probably heard it somewhere else too. What did we say? In pre-calculus, okay. You usually hear it the very first time in geometry, but you use it in reference to circles instead of in reference to functions, okay? Secant is the idea of having 2 points, and we're going to write this down here in a minute as well, having 2 points on a curve and finding a line between those 2 points, okay? So secant is this image right here. A tangent line is actually just a line that touches a curve. Okay, it doesn't cut through it like a secant line does. Sometimes I'll have students talk about how it sort of rests against the curve, or it kisses the curve. It's just the surface sort of attached to the curve instead of actually cutting through the curve. The tangent line. So tangent lines are actually what you're seeing happen right up here as well. That's what that blue line is a tangent line. So tangent lines have to do with calculus. A few more things. You have the average rate of change between a time A and a time B. So if you think about, most of you probably drive, and if you don't drive, maybe you run or you bike or something like that. You can find your average speed. If you have fancy watches, I have a watch when I run, it tells me my average speed, right? But I can also look down at any point in time and I can actually see my speed right now, right? When I'm all done, I can actually see the average speed, but at any given point in time, I can see my instantaneous speed. That average speed is a pre-calculus concept. What do? We add up all the distance we drove or we ran or we biked or whatever, and we divide it by how long it took us in hours or minutes or whatever we choose. If you're doing it with calculus, that process of averaging is not what you do to find your instantaneous speed. We do it differently. Curvature, okay? So in pre-calculus concepts, you did curvature of a circle. With calculus, we're going to be able to find the curvature of an actual curve, so it's more general, right? We've got things that are very, very specific that we can do in pre-calculus, and when we get to calculus, it sort of opens up more options, more things that can be done. When we are in pre-calculus, we're able to find the height of a curve. We do that just like back on this slide by plugging in the very first one, plugging in the x value, we get out the y value. That finds the height of a curve. But when we're actually finding calculus-related concept, we can find the maximum height. We can know exactly where it's the highest period. This is a really cool idea because if you're running a business, do you care about the profit at a given point in time? Well, yes, but wouldn't you like to know how you get the maximum profit? Yeah. So this is a very important concept when it comes to business-related ideas as well. Tangent plane to a sphere. Tangent plane to a surface. This is sort of the 3D analog to the one above where it was curvature of a circle versus curvature of a curve, right? You have the 3D pictures going on. When we're in pre-calculus, we can find the direction of motion along a line. And then when we're in calculus, we can do it along a curve. Again, we have more depth than what we're able to do. I think we've got 2 more of these. Okay. Area of a rectangle. You can do that without calculus, right? What's the formula? Length times width, right? We're going to come back to this area idea here in a minute or next time. But what we're able to do with calculus is actually find the area of a curve. Well, why does it make any difference? Well, that curve is not straight lines. So I don't have the geometric formulas. I might be able to use some geometric formulas to approximate, but it's only an approximation. But with calculus, I can actually give an exact answer for how much area is under that curve. Work. Without calculus, you can do work done by a constant force, right? A force that applies constant pressure, all right? But when you're doing with calculus, you could have something applying variable pressure. The pressure is changing in some fashion. It increases, it decreases over time. Without calculus, you can find the center of a rectangle. That's a geometric concept. You can do it in geometry. There's formulas to do that. But in calculus, you can actually do it for any shape. It doesn't have to be a rectangle. You can actually find a center of a rectangle. You might think, why would I care about a center of an object? Well, a center of an object has to do with balancing things, how things balance. That's where it's usually used as a balancing issue. You can find, without calculus, the length of a line segment. Like physically, you could actually take a tape measure and measure it out. That'd be something very concrete you could do. You can also use some algebra to do it, right? You find this point and you find that point and you use a distance formula, a little bit of Pythagorean theorem maybe or something like that. You can do that without calculus. But with calculus, you're actually able to find the length of any curve. It doesn't have to be straight lines. That's different. Because even with a tape measure, that doesn't work very well, right? Even if you have the little curvy fabric tape measures, you know, that the seamstresses use, it doesn't work very well for a curve. We're going to do some 3D examples. Without calculus, you can find the surface of certain objects, very specific objects, like spheres and rectangles and circles and, not circles, I meant spheres and, I went 2D on me all of a sudden, spheres and prisms, rectangular prisms or triangular prisms, pyramids, cylinders, things like that. You can find all those surface areas, no problem. Not only can you find their surface areas, you could also find their volumes. I'm skipping one here for a second. So the green object at the top is talking about surface area. The yellow at the bottom is talking about volume. Well, with the surface area or the volume, it's a specific formulas for specific objects. And a lot of objects that we use in our real life aren't that specific. Like, for example, when you talk about a can of soda, it's almost a cylinder. But is it exactly? It's not quite a cylinder, right? You know, the can of green beans is closer than the can of soda. So it's almost right, but it's not quite right. So with calculus, you can take those objects that don't have this very rigid description of what they are, and you can broadly find these different objects. So you can find the surface area, or you can find the volume of those particular objects. Okay, this blue one in the middle that I skipped, the mass of a solid of constant density, whereas it's compared that to the mass of a solid of variable density. So density means how if you will, we'll use weight for a moment. how the weight is distributed through an object. So if you have the first object over here, I mean, the objects look the same almost, right? It looks sort of fuzzy in the second object's picture, but they look the same. It's the same shape. What's the deal? Well, you know, just think about your own body or whatever. I mean, like, my hand does not weigh as much as my head, right? It's not a constant density. What's inside and how everything is situated inside matters. If you actually had a box and you had a gift wrapped inside and you had some objects that were heavy and some were light, not every part of that box has the same weight, is the same denseness in certain parts of that box. Okay, so calculus allows us to actually allow for that variability and still find the average density of the box, the mass of the box. They're using boxes. And then the last one is an example that you get to do this in Calc 3. This is a Calc 3 object right here. Finding the sum of finite number of terms. That you can do with Precalculus, and you probably have before, where it says, you know, add up the numbers from 5 to 50, you know, multiples of 5. You can do that, right? You can physically add them up. Well, what you can do with calculus, you can do that with infinitely many objects. We don't want to do that by hand, right? It's not possible. So you can do that with infinitely many objects. All right, so let me do one little bit here and then we'll stop. There are two types of examples that we're going to take a look at using calculus. We'll look at the first one briefly and we'll pick up with this one next time. We talked about the description of these two things, a secant line versus a tangent line. So if you want to fill these in on your notes, that'd be great. A secant line is simply a line that goes between 2 points on a shape. So when you first see secant lines, you do usually see them in a geometry and they cut through a circle, something like that. There's nothing special about a circle. We could cut through a curve like that as well. That's a secant line. It takes 2 points on the object, and it connects them with a line. Now a tangent line doesn't do that. A tangent line just touches the surface of the object. And it did it in Precalculus, like this. Geometry kind of stuff, and it will do it in calculus as well. So if I take any particular point right there, I'll go with that one. It's easier to use my line tool and put the point on afterwards. These would be tangent lines. Okay, so this is the objects that are different. We mentioned secant line versus tangent line, and we will explore this concept more next time and we'll pick up there. Okay.